So in the last lecture we started with what is image restoration. We have already seen what is degradation model and noise models. Okay, I'll just go through the basics again once again so that we can start with inverse filtering. So in the today's class we are going to see what is inverse filtering. Okay, so this you already seen that original image we are giving it to the degradation function. So this is degradation function which is shown by h of x comma y. This is degradation. Okay, and the noise is added to this. N of x comma y is a noise, and you get the degraded image which is given by g of xy. Okay, and this is your restoration function. Restoration function. Okay, and this is what you get, f cap x comma y. So what is this f comma x comma y? Is a restored image, right? This is restoration. So here now you know what is f of xy. F of xy is original image before degradation. So right before degradation, g of xy, g of x comma y, g of x comma y is observed degraded image. Then n of xy is additive noise, and small h of xy is degradation function. Okay, and what is f cap? I said f cap is restored image. Okay, so the figure is divided into two parts. Basically this figure is divided into two parts, degradation block and restoration block. Okay, so we can write this g of x comma y as integration from minus infinity to plus infinity f k L dot h of x minus k y minus L dk dl plus n x comma y. Okay, so this is equation number 1, which can be written as g x comma y f of x y convolution with h of x y plus noise x comma y, n of x comma y. So this is equation number 2. Okay, so in other words we can say that the original image, okay, we can say that the original image gets convolved with the degradation function given by h x comma y, and noise gets added to it. Okay, hence to remove the noise or remove this degradation function convolution, we need to apply inverse filtering, which is also known as deconvolution, okay, to the degraded image. Okay, so in the discrete domain, in the discrete domain, equation 2 becomes g of xy equal to summation kl, you can write hx minus ky minus l plus n x comma y. This is the third equation. Okay, now we want to find out, okay, now we'll see what is inverse filtering. Okay, so inverse filtering and pseudo inverse filtering. So we'll see what is inverse filtering. Inverse filtering, and after this we will see what is pseudo inverse filtering. So a way to get rid of the blurring. Okay, what is blurring? Why I am saying blurring? Blurring may be a degradation function. Okay, your image is blurred and you want to remove that blurring. Okay, so a way to get rid of this blurring is by applying inverse filtering or deconvolution. So we know that the input image f of xy gets convolved by a blurring function h of xy and changes to g of xy. Hence, to retrieve f of xy from g of xy, we take the inverse of h of x comma y. So g of xy is already, you know, it is given by this. Okay, now for simplicity we will assume that n of xy is equal to 0. The noise term is 0. That's what we are assuming here. Okay, so we will get g of xy equal to double summation h of x minus k y minus l f of k comma l. Okay, here I had okay, I have made mistake here. Here it should be into f of k comma l. Okay, don't forget, here I have written properly. Okay, here I have written properly, but here I had missed this. Okay, so here the noise term we are making it 0, so we will get this and we'll name this as 4. Okay, so now we have to take the Fourier transform. Take Fourier transform. So after Fourier transform, what we'll get is g of xy becomes capital G u v. Okay, so h of u v multiplied by f of u v. Why multiplication? Because here it was a convolution in one domain. Okay, this was a convolution, so it becomes product in another domain. Okay, so I want to find out f of u v. That is our objective. So what will be capital F of u v? It will be equal to g of u comma v upon h of u comma v, right? So this is equation number 5. Okay, so now we'll assume that, we'll give one variable, use one variable, let h1 uv is equal to 1 upon h uv. Okay, so therefore inverse filtering is given by capital F u v equal to, I will write this as this. Okay, so I'll get h1 u comma v into g of u comma v. Okay, so now if you take the inverse Fourier transform, so taking the inverse Fourier transform, we get f of x comma y equal to h1 x comma y convolution with g of x comma y. Okay, so that is what is the meaning of this. That is, if we convolve the blurred image with the inverse of the blurring function, we get back the original image. Okay, this can be further simplified by drawing a block diagram. Okay, so we can draw a block diagram here as f of x comma y, this is h of x comma y becomes g of x comma y, that is degraded image, and then we are restoring it back by applying h1 x comma y, and we will get f cap x comma y. So this is what is inverse filtering. Okay, now we had assumed that the noise term is 0. Okay, so what we got, capital F of uv equal to g of u comma v upon h comma uv, huv, right? Now if we add noise, so in presence of noise, g of uv equal to h of uv into f of uv plus capital N uv. So what is capital N uv? It is what? Capital N uv is the Fourier transform of noise, right? So here we can write this as f of uv equal to g of u comma v upon h of u comma v minus n of u comma v upon h of u comma v. Okay, which can be written as g of u comma v into h1 u comma v minus n of u comma v h1 u v. Okay, so this becomes which one equation number? This was 6, so this will be 7 and this is 8. Okay, now here n of uv, I told you n of uv is what? It's a n of uv is the Fourier transform of the noise term, right? Now if h of uv is 0, suppose, okay, is 0, then what will happen to this term? The term n uv upon h uv, that is n uv into h1 uv will become what? Okay, something divided by 0. Okay, what will happen? Can assume large values, right? It will be can assume large values, right? Resulting into amplification of the amplification of noise, right? Resulting into amplification of noise. Why? Because huv is 0, right? That's why. So this h of uv, that's what I said, 1 upon this h1 uv, right? 1 upon HUV will tend to what? Infinity, right? So this is highly undesirable. We don't want this to happen. So not desirable. But therefore inverse filtering is not regularly used in its original form. Okay, we will modify this. So the modified inverse filtering is known as the modified inverse filter is known as pseudo inverse filter or inverse filtering. Okay, so what we do here is we'll write this H pseudo inverse filter is equal to 1 upon HUV when H of UV is not equal to 0 and 0 otherwise. Okay, so what will happen because of this? This ensures that HPI does not become infinity when H of UV is equal to 0. Okay, so pseudo inverse filters gives much better results as compared to the inverse filters. In spite of this, both pseudo inverse as well as inverse filters are sensitive to noise. So now we'll see in the next session what is Wiener filter.